Okay, good morning all. So this
Good
is
morning, sir.
the first lecture of MTL 602 functional analysis course. So are all the students MSc students? Because I think this course is allowed only for the MSc students. Uh, so okay, so far 35 have joined. So let me first give some introduction about the course. So oh, you know the timetable, right? So the lecture classes will be 3 times a week on Tuesday, Thursday and Friday at 11 a.m. Tuesday, Thursday and Friday. And did you get any schedule for the tutorial class? Can anyone tell?
No, sir.
No, okay. So we will decide about the tutorial class. Maybe first week we will not have any tutorial, but from next week onwards, we will have. I don't know whether like you are divided into groups or there will be only one tutorial session. So I'll let you know about the tutorial classes later. And let me give you some reference books. So, so let me. So there are many like good books on functional analysis, but this is the introductory course. So I'll be trying to follow mainly from two books. So there is a book Linear Analysis by Bela Bolobas. So I'll start with this book, and for some part maybe I'll follow some other book. So the second one you can look at also Simmons' Introduction to Topology and Modern Analysis. So this book by Simmons, it contains topology also, general topology, which you have already done a course. So from this book, mainly like if you see part 1 is on topology. In part 2, so basically chapter 9 and 10 mainly we will be covering. You can look at chapters.
Hermitian operators, Hermitian operator.
Please mute yourself. Everyone, please keep yourself muted. Only when you want to ask something, you can unmute and then ask question. Okay, so mainly chapters 9 and 10. I'll see later if I have time, then I can maybe cover some other topics from other chapter from this. And You can also look at functional analysis by Krasik. So these are some books that you can refer. And about the evaluation policy. So, this semester also it's online semester, and there is supposed to be only one midterm exam and one major exam. So, the evaluation the midterm exam will be for 30 marks, 30% weightage, and major exam is 50%, and quizzes 20%. So, most likely we will have two quizzes. The date will be announced, and we'll have maybe one quiz before the first midterm exam. We'll have some time, and then we'll have another quiz between midterm and the final exam. So, any questions so far?
Sir, what are the prerequisites for this course? Like what we
Yeah.
should have?
So, let me write certain things which I expect that you should already be knowing. So, prerequisites. So I expect that you know about vector spaces, expected to have knowledge of vector spaces and linear transformation. So I hope all of you have done a course on linear algebra where you have studied about vector spaces and linear transformation from a vector space to another vector space. Then you should be familiar with the theory of metric spaces. So on metric space, you should be knowing about uh, what we mean by metric space, open sets, closed sets. balls of some radius r, closure of a set, interior of a set, and what do we mean by dense subset? Maybe certain things I'll also recall, but you can see if you like know these terms. Separable metric space, sequences and convergence. So convergence of a sequence in a metric space, continuity, and compact set. Uh, yeah, also, what do we mean by Cauchy sequence? And completeness. So let me write these, etc. So these are certain things which I expect. I mean, when I use some term, maybe I'll recall the definition, but you should revise these things to see that you are familiar with these notions. If you know inner product space also, it is good. Otherwise, anyway, I'll recall the main things about inner product spaces when we come to it. Uh, so vector spaces, metric spaces, a little bit of general topology, point set topology. So here, I mean, maybe we will need some basic things. So, but at least metric space, it is expected that you understand. And yeah, so main requisite is this you should have knowledge of vector spaces and metric spaces. Topology also, I'm sure all of you would have done the course last semester. So if I need something which is like more than metric space, most of the things you will see that that we will consider will be on metric spaces. So if you know about continuity and these things on metric space, that may be enough. But if you know general like continuity, compactness, these things for general topological spaces, then that is even better. Is it clear?
Yes, sir.
Okay, so let me start some basic things that we will be studying. So what we will start first thing is on We write normed linear spaces. So what do we mean by norm linear space? So what we'll consider is, so let V be a vector space over the field of real numbers or complex numbers. So in linear algebra, you might have studied that the vector space can be defined over any general field F, but here we will always consider that field is always R or C. So field is always R or C, and do you know what we mean by norm on a vector space? So let me define what is the meaning of norm. A norm, I'll denote by this, on V is a function from V to R satisfying so what are the properties of norm? First thing is that norm of x is greater than equal to 0 for all x in V, and norm x is 0 if and only if x is equal to 0. X is the 0 vector. Right? So norm is always non-negative, norm of a vector, and the norm of a vector is 0 if and only if x is the 0 vector. So this is the first property. Second property is that norm of any lambda times x is equal to mod lambda times norm x for all x in V and lambda belonging to the scalar f. So f is either R or C, so whatever the field we are taking. So you can see that here this is the reason that we have taken vector space over field of real numbers or complex numbers, because the this second property, you see, we are writing mod lambda. So there should be some notion of absolute value of the scalar to define this. Right? So if the field is real number, you know that absolute value of a real number is defined. Also for complex number, you know what is the absolute value of the complex number. But for general field, there is no notion of mod lambda. Therefore, uh, we cannot define norm. And it is possible to define on some other field also, but we will only consider R or C. And the third one is norm of x plus y is less than equal to norm x plus norm y for all xy belonging to V. So this third property is called, this is called triangle inequality. So you might have seen this before also. So these are three properties. If there is a vector space over R or C with a function which is non-negative for all vectors v and 0 if and only if x is the 0 vector. And second property is norm of any scalar multiple of a vector x is equal to mod lambda times norm x. And third is the triangle inequality, norm of x plus y is less than equal to norm x plus norm y. So a non-linear space, linear space is same as vector space. So by a non-linear space, we mean a vector space over R or C together with a norm defined on this. So V with norm, this is called a non-linear space. In short, we'll write NLS, non-linear space. So do you know some examples of non-linear space? Can someone give some examples?
Take the distance from the origin in the usual sense.
Sorry, what did you say?
Uh, we can consider like R2 and take the distance from the origin.
Okay, so you take R2 and take the Euclidean norm, right? So that gives you norm. So another thing is that if we have any non-linear space, then there is a induced metric. So this is also a metric space. So let me write this. So every non-linear space let me write V with norm. This is a metric space with metric defined as. So can you tell me what is the metric? If you know a norm, then how do we define d of xy?
Norm of x minus y.
This is norm of x minus y. Right? So once we have any norm defined on a vector space, we can also define metric as d of xy is equal to norm of x minus y. So this d is called the metric induced by the norm. By the norm. Right. So once we have any non-linear space, it is also a metric space. So therefore, we can talk about uh, whatever you know for metric spaces. Like if I have any sequence here, then you can talk about convergence of a sequence. You can talk about the continuity of function between any two non-linear space. So once we have the non-linear space, it's a metric space, and therefore it is also a topological space. So we can talk about all those concepts that you have learned for metric space or topological space. So is the converse true? So is it true that every metric space is induced by So if I have a metric on a vector space, maybe let me write as a question. Is every metric space metric on a vector space induced by some norm. So that is, if you have a vector space and you are given a metric on that, then is it true that you can define a norm such that d of xy is equal to norm of x minus y? So that is, if d is a metric on a vector space V, does there exist a norm on V such that d of xy is equal to norm of x minus y for all xy belonging to V. So the answer, as you can expect, is no, because otherwise every metric space will be the metric vector space will be a norm linear space also. So metric space is more general than normed space. So this is not true, but can you give an example of a metric on a vector space which is not induced by a norm?
We can take R and take it discrete metric.
Okay, so R with discrete metric, you claim that it is not induced by any norm. Can you say why?
Uh, because like I'm taking the field also to be R over R.
Okay,
So I can take like if it is induced by a norm, I like the distance between 5 and 7 will be 1 because
okay,
it is discrete metric, and the distance between 10 and 14 also has to be 1. But
okay,
from the properties of norm, the distance between 10 and 14 has to be twice the distance of 5 and 7.
right. So basically, what you can see is that uh, in general the answer is no, and but can we give some condition such that this is true? So is no. Let me write not necessarily. So for example, take R with the discrete metric, and then you can see that this is not true. So in fact, if you have any metric which is bounded, then I mean this will not be true, because You see, if we have a metric, then if I take 2 points as that the distance between them is positive, then if you take say distance between x y is equal to some positive number r, then distance between 2x and 2y will be 2 times r, because it is norm of 2x minus 2y. More generally, if I take any scalar multiple lambda x lambda y, then the distance between this will be lambda times mod lambda times distance between x and y. So if distance between x and y is positive, and if we take lambda arbitrary, then we will get mod lambda times r, which is unbounded. So what we see is that suppose D is induced by a metric, then we must have some condition. So suppose D is a metric induced by a norm, then what can I say about distance between, if I take lambda x and lambda y, this is norm of lambda x minus lambda y, because it is induced by a norm, and this we know by the property of norm is equal to mod lambda times norm of x minus y, which is equal to mod lambda times d of xy. So we have d of lambda x lambda y must be equal to mod lambda times d of xy. This is called homogeneity. So first is this property. That this metric space must be homogeneous. Uh, can you see that some other condition is also required? So we also must have translation invariant. Translation invariance. What do I mean by this? So suppose I take d of x plus z and y plus z. So we have 2 points x and y, and suppose I translate them by vector z, then I get x plus z and y plus z. Then what is the d of x plus z and y plus z? This must be equal to d of xy for every xyz in V. And again, the proof is very simple, because d of x plus z, x plus z and y plus z, this is nothing but norm of x plus z minus y plus z, and z cancels, and this is norm of x minus y, which is equal to d of xy. Right. So distance does not change if you translate the vectors by any given vector. So this is another property which must be true. So if you have I mean, this also gives you a way to check. Sorry, let me again connect this. Yes, so if you have a metric on a vector space which does not satisfy one of these two properties, then it cannot be induced by a norm. So what about the converse? Suppose I have a metric on a vector space which satisfies this 1 and 2, then can you define a norm? So conversely, suppose there is a metric which satisfies these two conditions, then is it always possible to define a norm? So conversely, suppose D is a metric on a vector space V, which satisfies one and two. Then how do we define norm? So then D is induced by norm defined as so I need to define norm of x. So for any vector V, how do I define norm of any vector x, norm of x? This must be defined as distance between x and 0, right? Because if you want that this norm induces the metric D, then we know that distance between x and 0 is norm of x minus 0, which is norm of x, right? So this is natural that this is how we should try to define. So now how do I show that this is a norm and the metric induced by this norm is nothing but D, right? So norm of x equal to dx0 defines a norm on V, and we also have to see that distance between x and y is equal to norm of x minus y. Because this norm must induce the metric D. So, so why is this true? So how do we see that this is a norm? So first thing is that norm of x is equal to dx0, because distance is always non-negative. This is greater than equal to 0 for all x. Also, norm x is equal to 0. This is equivalent to d of x comma 0 is 0, and distance between any two points x and y is 0 if and only if x is equal to y. So this is if and only if x is equal to 0. So the first property of norm is satisfied. What about the second property? Norm of lambda x. This by definition is distance between lambda x comma 0, right? Now we want to prove
सर
that
वीडियो नहीं आ रहा
sorry,
सर वीडियो नहीं आ रहा वीडियो
it should be visible. Is it visible to others?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
So
Yes,
maybe
sir.
you are having some network problem. Maybe I'll switch off my video, then it may.
ओके ओके सर
Okay, so now we want that this should be equal to mod lambda times norm of x, which is equal to mod lambda times distance between x and 0. So this is same thing as distance between lambda x and lambda times 0. And by the first property homogeneity, this is equal to mod lambda times d of x0. This is by 1, and which is equal to mod lambda times norm of x. So this is also satisfied. And the last one is the triangle inequality. So if we look at norm of x plus y, this is distance between x plus y and 0. We want to show that this is less than equal to norm x plus norm y. That means this is less than equal to distance between x and 0 and y and 0. So first of all, because d is a metric, this is less than equal to distance between x plus y and y plus distance between y and 0. This is by triangle inequality of the metric D. And now we will use translation invariant. So this d of x plus y comma y, this is equal to d of x plus y minus y and y minus y. This is by translation invariance, which is same thing as, so therefore this is equal to d of x comma 0 plus d of y comma 0, which is norm x plus norm y. Right. So what we get is that if we have any metric on a vector space, then that is induced by a norm if and only if it satisfies these two conditions, translation invariance and homogeneity. So hence, let me write this as theorem. Let D be a metric on a vector space V over F equal to R or C, then D is induced by norm if and only if D is translation invariant and homogeneous. If D satisfies these two conditions, then you can define norm x equal to D of x comma 0. And if it is induced by norm, then also we have seen that D must satisfy these two conditions. Okay, so now let me give several examples. What is the time? Okay, we have few more minutes left. So maybe I'll give some notation. So I'll follow these notations which are in book by Bolovas. So let X be a non-linear space the unit sphere of X is denoted by S of X, and this is equal to all those X in X such that norm X equal to 1. Okay, so far I had been using V for the vector space, but now I am using X for the vector space. So X is a vector space, and there is a norm defined on that. So the unit sphere is the collection of all the unit vectors. So unit vectors means norm of X is equal to 1. This norm is also called the length of the vector. So here we say that if the vectors of length 1, that is called the unit sphere, and this is denoted by S of X. We'll write closed unit ball of X. This is denoted by B of X, which is equal to all those X in X such that norm of X is less than equal to 1. So more generally, we will define uh, closed ball of radius r centered at x naught. This is denoted by BR X naught, or sometimes we write B X naught comma R. This is all those X in X such that norm of X minus X naught is less than equal to R. So you would have seen the similar notion in metric space. So ball of radius R centered at X naught is all those X such that distance between X and X naught is less than equal to R. This is closed ball. And similarly, we define open ball. So we'll also define the sphere SR X naught or SX naught R. X naught R. This is equal to all those X in X such that norm of X minus X naught is equal to R. In open ball, this is denoted by dr X naught or dx naught R. This is equal to all those X in X such that norm X minus X naught is less than R. I mean, in some book, this B X naught R is denotes the open ball of radius R centered at X naught. But in this book, that is the notation for closed ball, and for open ball, we are using D X naught R. So these are just some notations. Let me now just give a few examples, and we'll continue these examples in the next class also. So examples of non-linear spaces. So first example is we take X is equal to Rn or Cn. So when I write Rn we are taking vector space over R, and Cn is vector space over C. So maybe I'll write here Rn as a vector space over R, and Cn as a vector space over C. Right? So when we don't specify the field, then this is the usual one we are taking. And here we can define norm. So that is called the Euclidean norm. So norm of X. So if I take any X is a vector in Rn or Cn, so it can be written as tuple x1, x2, xn. And how do we define the norm? This is equal to summation of mod x I square, I equal to 1 to n, and take the positive square root. So this is the usual norm, and this gives you the usual Euclidean metric on Rn or Cn. So this all of you are familiar with, and you can try to prove that this indeed defines a norm, right? So the main thing would be proving the triangle inequality, that norm of x plus y is less than equal to norm x plus norm y. So by the way, in this book by Bolobas, I have started from chapter 2. If you see chapter 1, they have like proved some famous inequalities. So in that you will find this also. So it is called Minkowski's inequality, or I mean, this is a special case actually here for 2, but for general P also it is satisfied. So this is one example of norm. We can define other norm also. So in fact we can take this same vector space, and for any P greater than equal to 1, we can define the pth norm of this vector x. So there, instead of taking this power 2 and 1 by 2 raised to power 1 by 2, you take power p and 1 by p. So maybe I'll write again, x is Rn or Cn. For any P greater than equal to 1, we can define norm of x. I'll write P here. This is equal to summation of mod xi to the P and raised to the power 1 by P. And we can also define norm x infinity is equal to the maximum of mod xi, where I is between 1 and n. So in metric also you might have seen that other than Euclidean metric, you can define the metric, the P metric or infinity metric by these things. So these all defines norm on this thing. Let me stop here. In the next class, I'll give some more examples of non-linear spaces, and then we will look at some other results about non-linear spaces, and we'll discuss about the bounded linear transformation between non-linear spaces and so on. Okay, thank you all.
Thank you, sir.